Hi, everyone. Thank you for joining today's webinar on a new spin on particle analysis, introducing centrifugal sedimentation. My name is Julie Chen Nguyen. I'm your facilitator today, and I'll be monitoring any questions and comments. With me is your speaker, Dr. Mike Pohl, the VP of HORIBA Scientific. So Mike will be covering all the slides, including the Q&A session that we're going to have at the end of the presentation. All right, I'm going to pass the ball to you. Thank you.
Okay. Well, I'd like to thank all of you for joining us today. This is a sort of a topic that may be considered to be somewhat old in a sense that, looking at sedimentation has been around for well in excess of 100 years now, and people might wonder, what's new or exciting to learn here. But what we hope to do today is to take you through some of the considerations when you decide to use this technique, show you some of the new features we've come out with our new CN300, and then we're going to show you some actual world samples that we ran so you can see how the features and benefits we think we've built into this instrument might be able to do something for you in your application. Okay, now when we go to talk about Stokes Law, one of the things we have is certain restrictions on where this will be operative. We're going to show you the equations in a moment, and the equations are really quite straightforward, nothing particularly exciting about them, but in the background, you're going to have to remember that these conditions on this slide have to be met. As we're doing the measurement for the sedimentation, we've got to have a laminar either flow downward or sedimentation, or creaming if you're dealing with emulsions or things like that. You cannot work at all with very large particles. They simply will always be in a turbulent flow situation. And so these equations will not be applicable. You're going to have to pick a type of radiation, because what you're going to do is you want to measure the concentration of the particles. And for that, we'll show you we're going to be using Beer's law. But again, you have to have something that is actually being absorbed by the particles. Your particles also must be adequately separated from one another. One of the problems you run into, especially with very small particles, is these particles, you have to put them in there at a reasonably high concentration, which means the particles get close to one another. And the limitation is going to be that if you have less than 6 solvent molecules between your particles, you're going to end up with what is called hindered settling. What is happening if the particle is sedimenting downward is, as that particle sediments downward, it is displacing liquid that used to occupy the space that it's moving into. And so that liquid, as the particle pushes down, is going to go up around the side of the particle. And so if your particles get too close together, that liquid that is going upward is going to influence the next particle or the neighboring particle, and it's going to end up rising when it should just be sitting there while the other particle sediments. And so what will happen is when particles, in this particular case, rise, that's going to end up looking to you like much smaller particles than they really are. And so again, there are equations, things you can do to avoid all of these situations, but we don't really have time to get into all of those equations today. So we're just going to show you kind of the practical side of this, what you're going to get out of it when it's set up properly. And then last but not least, also with the small particles, you're going to be in a situation where you're going to have Brownian motion in addition to sedimentation. And Brownian motion causes the particles really to move in 360 degrees. And you cannot really tolerate that because you're calculating how rapidly the particle settles when all it does is just sits there in gravity and settles down. So again, we'll show you some examples and talk a little bit more about this in later slides. Now, this is where it all starts out. The equation we have set up here is really for gravity sedimentation, where, as you can see on the right-hand side of the equation, you would have essentially 1g of gravity. We'll also take a look at centrifuge situation, where instead of 1g of gravity, you can select a number of g's by selecting the centrifuge speed. So we'll show you the benefits and some of the things that our new system can do there. And the whole idea is you really want this particle, you can see due to in this case, we put centrifugal force causing the particle to move down to the bottom to the detection position. And then we will be able to report the particles, and the detector will allow us to tell you the concentration. So we're going to have two measurements to make. We're going to measure time, which will tell us size of the particle. We're going to look at the light intensity in this particular case, and that'll be used with Beer's law to measure concentration. So relatively straightforward. You can see what we're going to input. We're going to put in particle density, the liquid density, solvent density, and the solvent viscosity. And so, the equation itself is not very hard to solve. The particular way we wrote it is not really typically how you would use it. Typically, you're going to be measuring the settling velocity for the particle. You're going to input these other three parameters, and then you're going to solve for, large D, because you really want to know the diameter of your particle. But the way it's set up, if you knew the size of the particle, you could actually predict how long it would take to sediment all the way down to the detector. And as I say, when we show it later, we're going to show it to you solving for D, which is the typical way we proceed ahead. Okay, so here what we're looking at now, we've come around to where we're going to focus really on the centrifugal sedimentation. To be honest with you, most of the particles that we look at nowadays are things which are very small, number one. Number two, very often very low density materials, or when I say low density, I mean close to the density of the fluid itself, maybe water in most cases. And so what happens is if you tried to do this with the first equation where we only had 1g of gravity, you could be spending hours there waiting for this sedimentation or creaming if there was an emulsion that rise up. Again, most people don't have that kind of time. We're hoping to get an answer for you in 5 minutes or something like that. And so here you can see from the equations all the kind of things you input into the equation. A lot of them are fixed for the instrument when we build it. These detection points, the distance from the center, those kind of things, those are all built in. Every instrument is identical. We just put those in for you. You're going to, put in again the parameters you need, which is your densities, two densities, and your viscosity. The rest of it's going to really come out for you from the way you set up the centrifuge. So you need to know that omega, because that's going to determine how many G's of gravity are causing your particles to settle. And so, again, as you can imagine, this is a totally automated system run by a PC. All these equations are built in. You put in the parameters for your particular situation, the particles you're interested in, and everything else is done for you automatically. We'll show you how you set it up here in a moment and give you a little bit better understanding. But this is the direction of the rest of the seminar. Is this is mostly what we measure nowadays. I mean, you can measure lots of different things here because you have variable centrifuge speeds you can select, but in most cases we're looking at much smaller things where we're going to worry about using the centrifuge up to, as you can see at the bottom right there, up to 18,000 RPM. Now, the other side of the equation is what most everybody would know just as your typical Beer's law measurement. In other words, we're going to set up a measurement. We're going to have the particles in there. We're going to have it could be a beam of light, could be an X-ray beam, could be a variety of different things going through this flow cell that we have set up, or it could be a cuvette in certain circumstances. And what you're going to be doing is, number one, in your Stokes Law equation the Beer's Law equation at the bottom, the L, I wanted to start with L. L is actually going to be your path length. B is going to be your concentration. And then epsilon is going to be the extinction coefficient for your individual particles that you're measuring. So again, very simple and straightforward. You just measure concentration by Beer's law. You measure size with Stokes law. Now, as we're going to do this measurement, there's certain things you've got to pay attention to right from the start that are going to be very challenging type things. One thing is if you have particles of different density, they're all going to be settling at different settling velocities, and you really can only measure, these numbers we talked about, the time it took to settle and the concentration of the particles that had settled. So, if you try to do mixed densities, there are certain circumstances you can make this work. If the two size distributions happen to be very, very different from one another, you can first have one particle settle and do the proper calculations for that particle, then have the second particle settle, do a different calculation with a different density, things like that. So there are some cases you could make this work, but it's definitely very challenging when you're dealing with, mixed density materials. Another thing is Brownian motion. As you start getting down, really below about maybe 5 or 10 microns, particles are going to begin to move in different directions as a function of time and not just settle like you want it to do for Stokes' law. And so you're going to have to figure out at what point you can now no longer trust your sedimentation data to be pure sedimentation, because you can't have two different types of equations operating, or two different forces operating on your particles at the same time and have Stokes' law work properly. So, again, it's the kind of thing, certain techniques go all the way down very small in size and use Brownian motion for the entire measurement, but where we're trying to operate, we've got to stay away from Brownian motion. Now, when we go with the centrifuge, we have one benefit working for us, and that is the fact that you now have more than 1 g of gravity causing it to settle. So because you're putting more force on it, you're going to have a lot more sedimentation velocity than you are Brownian motion. So one of the reasons people like the centrifuge is you can certainly go well below 1 micron. We've run well below 0.1 microns, even all the way down to about 10 nanometers. So that's a benefit when you switch from gravity to the centrifuge. Again, we talked earlier a little bit about the hindered settling. You got to be careful you don't get too many particles in there so that you affect your data. One of the things you battle, as we mentioned earlier, with the gravity settling is going to be a slow measurement. If your particles have a nice high density and you're in water and so forth, those will settle very nicely for you by gravity. But any of the lower density type materials and much smaller particles are going to be a real challenge for you there. For the gravity settling, one of the things you'll often see is what they will do is to speed it up. They're actually going to measure. They're actually going to move their measuring cell into the X-ray beam up and down, because what that allows you to do is you can go to the position where the large and small particles are separating from each other, rather than waiting until they all get to the very bottom of the cell settling out. And so that's one way to speed it up, but not quite as fast as using the centrifuge. Another case would be you might have particles that are non-absorbing. We mentioned earlier the organic particles. Many of them have a refractive index very close to that of water, so they don't absorb, in this case, X-rays very well. So again, you're going to have a challenge measuring those. Again, your light gets around a lot of that because the light will be absorbed or blocked by the particles, and you have a chance to measure those. And then last but not least is a need for temperature control. You might remember when we looked at Stokes' law, we talked about the need to have the viscosity for the fluid to put into your equation. And the problem with it is if you don't control temperature, your viscosity will be fluctuating throughout your measurement. And so on the next slide, we'll be able to take a quick look at this. Here you can see I just sort of stole a little something from the CRC handbook for a typical type liquid. And what you notice here is, your temperature does not have to change a whole lot to see quite a bit of change in the viscosity. And so if your temperature is drifting, typically it will be drifting higher during the course of a run. You're going to have put in too high of a viscosity into your Stokes law equation. And so you can see the thing you want to do is try to keep this temperature as controlled as possible so that you would have a constant viscosity over the entire measurement time that you're, actually in the centrifuge. So again, this is something you want to pay attention to, and we'll show you some of the features again in the new instrument we have that will help you with that. Okay, so in the operation, here's again, we're going back to what we input as well as what's going to come out. As we mentioned earlier, we're going to be measuring time for settling. That from Stokes Law will give you size, light intensity over time, which will give you from Beer's Law the concentration. Now, we showed you the 3 parameters you need to input. Now, as I was just pointing out on the previous slide, a lot of these numbers you can just look up in your CRC handbook. I mean, liquid densities, even as a function of temperature, pretty easy to find. Viscosities can be found, and the particle size, the particle can also be found there, the density. So in many cases, it's not that hard to input this, and you're away and running and put your sample in, and out will come your data. If you can't find it in your CRC handbook, or gosh, there's all kind of references for all kind of dyes and pigments and all sorts of different things. If you can't find it there, you can actually measure these with other instruments in your laboratory. These would be things that you would have readily available, typically graduated flask or a cylinder, measure the density of the liquid, the viscometer to measure its viscosity, and a pictometer to get the particle's density. So even if you have a new experimental material, something that is not well known in the general literature these days, you can go back in your lab, make a few measurements. Most of these are a few minutes at most, and you then will know what equations to put into your Stokes Law and your Beer's Law so that you can get out some meaningful information. As I say, with most instruments, this is run by a PC, meaning all calculations, all data presentations, anything you want to see from the analysis of your sample is readily available. You can look at size, which is the most obvious. You can look at settling velocity if that were of interest for you for some reason. So you have all the information stored from the run, and you can pull that up if you want to do something different with the information. Okay, now we're going to start focusing what we just got done talking about on the new instrument, the CN300. You can see it here with the lid open. Certainly the biggest thing about this is the fact that you can't really tell it from what you're looking at, but this is a very heavy instrument because the walls have got to be able to retain any sample, any glass, should something happen with the cuvette that you're using to make your measurement. So it's guaranteed that even if you're at 18,000 RPMs and your glass totally shatters, it's all going to be held right inside that instrument. So you don't have to worry about being injured or anything happening. Obviously, the liquid's going to end up being spewed all around inside your centrifuge there, which is not particularly convenient. But again, there should be no damage to anything there, no people in any danger. So that's one of the first features, is certainly the safety of this instrument. Then the next one is the cooling capability, as we talked about earlier, especially using organic type samples, things like that. You're very often up at 18,000 RPMs, and so there you've got to get this temperature cooled down because it's generating quite a bit of heat. Peltier type cooler in there to get the air cooled that's around the centrifuge, so it's not allowed to heat up. It does take a few seconds to kind of come to an equilibrium temperature, but once you're there, you can do runs for half an hour, 45 minutes, and still be at the initial temperature that you set in. Again, the 18,000 RPMs is to do a good job on the smaller particles. You don't want to be standing around for hours waiting for your answer. You'd like to be able to get it quickly. So that high speed helps out quite a bit there. We also have built into it a gradient mode. This is very critical when you have broad distributions of particles or mixtures of different sizes, things like this. Again, we'll show you an example and why it's so critical, but again, it's put in there to allow you to speed up your analysis. Everything here, the thought is sedimentation takes too long. If you've ever worked with gravity sedimentation, I've seen samples take 45 minutes, an hour, even more to do one analysis. And then when you're done, you probably would want a second piece of data. So now you got to go in there and, do another measurement and so forth. And so you can really quickly chew up your day doing just a few analyses. Here, you should be able to do several per hour. We'll talk in a moment a little bit about there's really two ways to run sedimentation experiment. One is homogeneous, where all the particles are uniformly mixed in your cuvette. The other one is line start, where all your particles are going to come lined up on the top of your cuvette and are going to work their way toward the bottom. So these are essentially different type measurements, still Stokes Law, nothing really changes, but you'll see there's certain advantages to each of those. Certainly one of the nice features is even though we're going at 18,000 RPMs, it's very quiet. You can hear the person standing next to you talking in a somewhat normal voice. So, you don't have to worry about how many decibels are coming out or anything like that. And then last but not least, we have flexible type data that we can present to you. And we'll give you a few examples of those here in just a moment. So here we're going to take a look at the two types of measurements that you make. The one in front of us now is the one for the homogeneous measurement. If you look over on the left-hand side, you can see starting out with the measurement, everything is just uniformly distributed throughout your cuvette. As you begin to spin the cuvette, what's going to happen is the large particles are going to settle most rapidly. You're going to see a little bit of a buildup of large particles below the light source. Second, the medium-sized particles will work their way down to the detector and be measured. And then last but not least, the small particles will come down. And so you can see your raw data is in the middle of the slide there. It's going to be absorbance, which is what's coming from your light detector. And the other one is going to be time. So at the end of the run, then your computer is going to go in there, look at this data, calculate Stokes Law, Beer's Law, come out with a distribution of particles as a function of time. Now, the challenge you're faced with here, you might ask the question, well, why don't I do everything that I need to with homogeneous? The problem with it is that when you do this and start them all mixed up, sometimes they're not exactly homogeneous in that cuvette at the start. And so, you may have, from shaking the cuvette, you may have some movement in that cuvette itself. And so if you don't start out with totally homogeneous, you're not going to see these nice clean breaks. I mean, in our little graph we made up there ourselves, I mean, obviously it looks real clean. First one, then the other, but it's typically not quite that clean. And so, that's the reason we'll look at the next one. But the other thing I want to point out to you on the far right there, that's kind of important, is that you take notice if you look at the bottom of that cuvette, that's where all your particles are. And those particles have seen a lot of centrifugal force, especially if you spun it at 18,000 RPMs, you're talking about thousands of Gs. Don't ever try to just shake up the cuvette and run it again. You'll never get repeatable data. Agglomeration happens, particles stick to the bottom of the cuvette, the walls of the cuvette. So, I mean, when you go to do a sedimentation type experiment, typically you want to just throw the sample away, clean it out, and go on to a second sampling from your original material. Don't try to reuse it because that's going to give you some lousy data. And here you can see the other method, the line start method. It looks really nice and clean here. Obviously got the very large ones at the bottom, the medium-sized ones in the middle, and the small ones on the top. And that's, again, the goal you're going for is you want to introduce these particles and get them all to come down, as a nice line, so to speak. And so one of the other things you're going to do here that you wouldn't do with the homogeneous is that you're going to put a density gradient fluid into the cuvette, so that what will happen is you'll want the highest viscosity fluid on the top and the lowest viscosity fluid on the bottom. And again, what that does for you is that you're going to have the particles separate nicely going through that higher viscosity liquid, so that the large ones come out first, then slowly the medium size will work their way out, and last but not least, the small particles will work their way out. But then once you get them separated up at the top, you don't need a whole lot of viscosity to keep them separated later on. So again, to speed things up, what you want to do is get them nicely separated, then go ahead and analyze each one of them as they arrive at the detector. And here you can see if everything were to work correctly, you would see three distinct peaks: a large peak, medium-sized peak, small peak. And so, this is the optimum way if you want to get things resolved. Important in a lot of cases, polymers, many times you're going to make blends of materials to get your final polymer that you want. You're going to need to, in the polymerization process, you want to look at, the original starting material, the seed crystals. You want to see dimers, trimers, tetramers, things like that. So lots of cases where these kinds of mixtures are going to exist. And then down at the bottom, you can see, it's a little bit tricky to make these density gradient fluids. And so what we did is we have an option where we will do that for you. One of the typical cases we do is we work with sucrose, essentially sugar and water. And, we then put that mixture into the cuvette and we make it up in this density gradient fractionator. And so now you've got exactly a known density gradient, again, information that the computer knows what it is. So it can tell you what the viscosity is all the way down as you're going from the top of the cuvette all the way down to the bottom. And so this is kind of a nice feature. You don't have to sit there and try to make these by hand. It does this for you. It's got some, syringes there that allow you to get a nice gradient produced. So again, this is the other mode of operation, the line start mode. Again, same thing on the right there. These particles, even though they're separated, they've been kind of, compressed down there at the bottom of the cuvette. You certainly don't want to ever try to reuse those solid particles to make a second measurement. You would have no chance of getting any reasonable type of data. So again, we talked a little bit earlier about this, the gradient acceleration mode. And you can see here we have a mixture of two sizes, perhaps three sizes of particles. And the big thing is, again, you don't want to sit here forever. So, for example, the peak on the right, which is circled in red, that particular peak you might want to measure at 1,000, maybe 1,500 RPMs. And the problem with that is if you run the entire sample at that speed, that much smaller particle below 0.1 micron, those particles are going to take hours to settle in your cuvette. So what you do is you start out, essentially ramp up your speed. You can see on the right there, first the large particles come out as you're ramping up. Then it keeps going up to 18,000 RPMs, and now your smaller peak will show up and we can measure that. The problem you're going to have if you say, oh, well, geez, I'll just be smart and I'll go ahead and do 18,000 RPMs at the beginning. The problem is that's large peak of particles, which is pretty small, but the large particles are going to end up being settled before you ever get the centrifuge up to speed. So you're going to end up missing all the large particles completely. And in many cases, those are the particles you're interested in. They may be agglomerates, they may be some tramp materials that got into your sample, things like that. So, you certainly don't want to miss those. And the way to do that is with this gradient, because you can go all the way from the large particles all the way to the small particles. Again, your instrument knows exactly what number of RPMs it's at. We'll show you how it does that in a while, but so it can do the calculation for Stokes Law just as if it was running at a constant speed. And so this is a very nice feature, especially when you're doing the line start. With the line start, you're assuming you're going to have multiple peaks. And so in most cases, those would be run with the gradient. And so here you can see how the measurement is actually made. On the underside of your disc, there's an LED down there, and the light is shining up to hit a detector up above the cell, up above the centrifugal disc. And then you're going to have open spaces in your disc itself where you can put your cuvette in there. And so what you're going to do is you're going to fill up a reference cell with the liquid that is in your sample cell with no particles in it. That's going to serve as a blank for you. And then you're going to put your real sample in the other cell. And so as this is going around, what's going to be happening is that first you're going to measure the sample, and a fraction of a second later, you're going to measure the reference cell. You'll subtract the value from the reference cell from that you measured for the sample. So any effects of liquid or anything possible like coloration might be in the liquid, all of that is essentially going to be blanked out for you when you make your measurement. So the other benefit to this is what happens is your detector can sense every time the light is coming up through the cell. And so it's just sitting there saying, okay, every 2 times that I see light coming up from the cell, that means 1 revolution of my centrifugal disc. And so by just sitting there over time and counting how many times that centrifugal disc has sent a signal up to the detector, you now know what your number of RPMs is. And this is how the gradient mode operates. It's changing, well, all the time to get up to 18,000, and it just stays there. But this allows you to monitor continuously what that centrifugal speed is so that it gives you accurate determination of Stokes Law. Now, here's an example just showing some repeatability. As you can see on the right there, this is a CMP slurry. This is a homogeneous solution, and CMP typically is very small, somewhere, a little bit less than 1/10 of a micron, all the way up to as large as 2/10. And again, these are obviously representative samples taken out of your beaker full of the CMP slurry, run 1 time, disposed of, a new one put in, run again. And here you can see the average sizes that were obtained. You can see very repeatable data, very low coefficient of variation. And so, very reliable data. And again, you still have the ability, if there had been something large in there, you would have seen it. If there was something small, it would not have returned to the baseline. And so you know that you have your whole distribution right there for this material. Now, these are certainly real world samples that actually our customers are, analyzing every day. These are some carbon nanotubes. When you make these, typically you're going to have some free unagglomerated nanotubes, but you're also going to have some in a bundled kind of agglomerated state on the right there. And again, you can see here's the power of the line start method is you can first, as the centrifuge is accelerating, you can see these agglomerated states, get an idea how large some of these bundled states are. And then finally, when you wait long enough and get up to 18,000 RPMs, now you see the actual free state or the crushed state of the carbon nanotube. And so, this is very important because in many cases, the bundled state would behave differently than the crushed state. And so you would, want to be able to differentiate how much you have there. You might even want to do some kind of a filtration to get rid of the bundled ones and only have the crushed state. You could see when that peak or that very broad peak at the right actually disappeared, and then you would know you had only the small free carbon nanotubes. So again, some of the power of the line start method. Now here, this is kind of a slide everybody who does this kind of a measurement always shows, is the power of resolution of, the instrument. On the right, you can see we synthetically made a mixture of these polystyrene lattices. You can see going from 100 nanometers up to a little over 1 micron. So, you go through, obviously run it, and then you can see we put 5 materials in there. We got 5 individual peaks. The software, what we elected to do here, a little bit unique, instead of figuring out what percentage of the total sample was in each peak, we just looked at the area under the peak as a function of each peak. So the largest area peak was the one at 0.153 microns, and that we set as 100%. So that was the largest peak. Then the one to the left, the one at 102 nanometers, that one wasn't quite as large. That one was 91%. And then the larger peaks at the bottom, you can see were 35, 25, and about 22%. Again, you could now, if you had paid attention when you were mixing these together, you could now determine the actual relative amounts of each one of those 5 peaks. Because again, in mixtures of materials that are polymerized, very often you do have different sized particles that are mixed together. And so you want to know how much you got into the blend before you actually made your final product. So again, a good example of the strength of resolution of this technique. Here's another example of what we were asked to analyze by our customer. This is a battery application. In this particular application, you had a center core of a particle, which was surrounded by some carbon. Sort of looks to me like what I would have thought of as toner. And of course, the big question with this and with toner as well is you want to know what's actually in the bottle that you're working with. In other words, how much is the individual particle, carbon particles on the left? How much are the agglomerated carbon particles in the next peak? How much, or what you really want, which is the NCM with a nice almost single layer of carbon black around it. And then what particles to the far right have also got some loose carbon black bound to that material, that battery material. And so you can see here, we started off and then we made a run green peak just to see what we started with. And you can see we applied some mechanical energy to it, and that then became the purple peak. So we had lost some of the carbon off the surface of the original particles. You can see we had more of the particles we actually wanted to have that had almost a sort of monolayer. But then obviously, because we knocked off the, some of the carbon black, we only had a very little bit left there at the very small end of the purple peak. So, we were able to show them where they were and how close they were to the ideal particles that they wanted to produce. The last one, this is an example from CMP slurry. This is a Japanese company who makes the precursor silica particles to prepare CMP slurries. If you know anything about that industry, the slurry itself is almost kind of a witch's brew of chemicals. They dump a bunch of stuff in there to keep these particles separated and, the right size and not aggregated, things like that. And you can see here there are 4 different grades which they sell commercially. The PL10H, which is the largest, all the way down to the PL1, which is the smallest. And so, you can see here with our centrifuge, very easy to make the measurement. You can obviously see that there's some overlap, that even when they're selling you PL10H, you're still going to have some of the 118 nanometer particles in there as well. Not surprising, because this is actually done in a kind of an agglomeration process where you start with the small ones and you agglomerate them into the big ones. So very, very good representation. And here you can see the actual parameters that are quoted for the particles. very, very close to the data which we had gotten for them. And there you can see some of the primary size particles. Remember, we're going to aggregate those together so you can see how many secondary size particles are there and what the aggregation ratio is. So, these are designed, these are kind of custom CMP materials that are designed for specific purpose with a specific particle size to the silica. So I think I'm running over here. We probably ought to just wrap it up and turn it back to you, Julie.
Okay, thank you so much. So, question 1. So, how does this technique compare to field flow fractionation?
Well, it's one of those things where it's, predicated upon the same equations. The way they elected to set up field flow fractionation is a little bit different than this, because they're typically always looking at relatively small particles, but you're still talking about the same principles applying, just a different instrumental design.
Got it. Thank you. Question 2. Can this technique be utilized in high concentration asphalt emulsions?
If you wanted to do something like that, probably the best way to try to do it would be to do it with the line start, because there you're going to separate your particles. Typically, at least those emulsions that I've seen have been a little bit too high in concentration. And so if you tried to do it homogeneous, you would end up having too much light obscuration and you couldn't make your measurement. So the other thing you can do, you can also do a dilution step if you feel comfortable with that. Some people feel that, when you make a dilution, that there's always a possibility you might cause things to agglomerate or otherwise the size to change. So that's the risk you run with dilution. But if you have a relatively stable emulsion, you may have an opportunity to do that without affecting the size.
Thank you. How does this technique compares to others, such as laser diffraction?
Well, the thing that happens is basically you're making measurements using different scientific principles, so to speak. So, you're going to expect to get reasonably similar data, but there would be a possibility, you might pick up some smaller ones with this than you could see with laser light scattering, for example. You might have a problem if you had some large ones that you would again miss them. So, you would expect similar data, but it's not something where you would hold it up to the light and they would superimpose on each other. They'll be similar, but not identical.
Thank you. What about polymers? Is this applicable to isolating large polymer molecules with low concentration in the sample?
Yeah, that's one of the things we didn't really touch on, but if you do the line start procedure, essentially you're doing a separation of the large ones from the medium ones from the small ones. And so if for some reason you said, geez, I want to look at these few big ones that came down, you could stop the experiment in the middle and pipette off the large ones that are on the bottom and study them separate from the entire distribution. So that's one of the other kind of benefits of the line start, is you could actually look at the particles that were separated, or you could let two different sizes settle together and look at the two of them together. So you actually are getting a separation of the particles by size in addition to getting the size of the particles.
Thank you, Mike. So we talked about high concentration. This person would like to know, what is the lowest concentration limit for measurement?
Well, again, that's going to be determined by your light source that you're using. Because when you go to use any kind of a light source and a detector, you want to be in the linear range of its response. In other words, if you get too high in concentration or too low, you're no longer going to be linear, which means that Beer's law is not going to hold. So the instrument itself knows what those limits are. And when you go to do the run, it will tell you if you've gotten outside the acceptable limits.
Okay, perfect. Can this tool separate the primary and secondary particle of the Fuso abrasives. So is the PPS and MPS you show in the last slide measured by this tool?
Yeah, that's how we actually measured them. Now, you may remember from that slide that there was actually a fair bit of overlap between some of the sizes. So, if you had them, these were the individual particles measured all by themselves. This is not a mixture of 4 different things in one cuvette. This is each one being measured separate. So if you had these mixed, let's say go to the far right, the 118 nanometer and the 229, you can see you would get kind of a messy sort of a distribution because there's a fair bit of the 118 nanometer in the 229. So, you would probably still see 2 peaks, but they would be strongly overlapping peaks that, you might have to use some other way of deconvoluting them if you wanted to figure out how much of the 118 nanometer and how much of the 229 nanometer you actually had in your sample. So, and the same thing even with the 12 nanometer and the 36 nanometer, you can see there's a fair amount of the 12 nanometer in the 36 nanometer sample. You won't be able to resolve them. This is going to be one massive distribution with 2 pumps in it typically.
Thank you. And this person asked, what is CMP materials? Is the chemical mechanical polishing materials? And in this case, we're looking at silica. Can this technique be used for virus-like particles, full
Yeah,
versus empty?
yeah. I mean, CMP is, fairly straightforward. It's silica particles, alumina, ceria, things like that. They're very discrete, nice, hard particles. But you can also do it. We've done things with viruses. Again, big disadvantage is it can take you a long time to get all of them to settle at 18,000 RPMs. But we've run a number of organic materials. What you're seeing is, as a company, as we evolved, we started out doing material science. So the examples we have are a lot of material science type materials. Later on, we got involved with some of the other technologies doing things for life science type applications, things like that. So we don't have quite as much experience with that kind of material, but there's no reason it can't be run, especially because we have the good tight temperature control so you don't end up in any way damaging your particles.
I would add though, if you're looking at virus, likely you would be interested in looking at particle count, the number of virus per mil or in a given volume. So we do have a different technique called the multi-laser NTA that may be more suitable in tackling applications like virus than in this case sedimentation.
Yeah, I think that's a good point, Julie, because there, what we're really doing is we're doing what we talked about earlier, which is we're measuring Brownian motion. So
Mm,
we're no longer trying to sediment anything. We just watch the particles move, and from the speed of their movement, we deduce the size. So you're right, you would get concentration, plus you would get particle size, both from one instrument, which you would not get from a centrifuge.
thank you. Okay, so the next question is, what is the minimal volume needed? And the second part of that question is, how much time does it need for one sample measurement?
Well, in terms of the normal configuration, we just use, cuvettes that are standardly provided by some of the glass companies. So obviously they've got to stand up to 18,000 RPM. So it's not some just Pyrex glass or something like that. But as long as it can stand up to it, we can use it. Typical volume we put in there probably be 7 to 8 milliliters, something like that. Now, there's all kinds of tricks you can play if you have a very rare or, expensive sample. You can actually put something in the bottom of the cuvette to occupy some volume so you didn't need so much liquid there in the first place. So there are things like that. You can do special measurement cells that are available, but a standard sampling with a normal cuvette that comes with the instrument would be about 7 to 8 cc's.
Thank you. Okay, so this person has more specific questions regarding to the software. We can definitely address that privately using labinfo@horiba.com, and we'll reach out to you as well. But basically, he's wondering if the software is compatible with, say, LIMS package. And the second part to that question is there an automated, like auto sampler that would allow you to measure samples in a high loading, high speed manner?
Yeah, I'll just do the second one first because simple answer, no, we do not have any automation for this simply because there is so much involved with getting the sample cell set up, getting it put into the centrifugal disc itself. It's just very, very difficult to try to do that in an automated sort of a fashion. In terms of can you use LIMS to transfer this data or take it to another computer or something, we have one package today that does that, but I wouldn't want to guarantee that that's going to work for all LIMS packages. So we'd probably have to talk one-on-one with what the individual had in mind to use, and then we could better answer the question, although we do also have a programmer here on site that if the company's computer folks could work with us, we can certainly write a package to allow it to go to a LIMS system that it doesn't go to today.
Got it. Thank you. But you can certainly reach out to us at labinfo@horiba.com. So I think the time is up. I want to honor your time and everyone else's time as well. Is there anything else that you'd like to add, Mike, before we close the webinar?
No, I'd just like to thank everybody for spending an hour with us, and we'll answer any questions you send our way for sure.
Absolutely. Well, thank you, everyone. And thank you, Mike, for the excellent talk. Don't hesitate to reach out to us. So on behalf of our Particle group, thank you for attending, and we will see you at our next webinar. All right. Thank you so much. Bye, everyone.